This is a conical tank with the following dimensions: 4 meters in radius, 12 meters in height, and it contains water. At this particular moment, water is 9 meters, the surface of the water is 9 meters from the vertex. Water is being expelled out here, and the flow rate is given as 1.5 cubic meters per minute. So from our basic knowledge of geometry, what do we know about a cone? We know how to obtain the volume of a cone, which can be obtained by this formula. Volume of a cone is equal to pi over 3 r squared times h. So this represents the volume of the conical tank and also the volume of the water inside the conical tank, because water is a liquid. It shows the shape of its container. So the volume of the water inside, if you know the radius, for example, water is actually here, you can get the radius, you can get the diameter and then get the radius, you know the height, 9 meters, you can actually obtain the volume of the water at this particular moment. But at this particular moment, all of those are changing. The volume of the water will change, that R will also change. For example, it's already here. Later, R will be smaller, and then H will be smaller than 9 also. So all of these variables are changing. So we are going to use derivatives to determine the change of these variables. And we know that to obtain the rate of change of these variables, we are going to get the derivative of this function with respect to time. Now, if we pursue on this, we are going to take the derivative of this function with respect to 3 variables. So here we're going to apply the chain rule. So for the chain rule, we can represent all of this function, this whole function, as u. So to take the rate of change of the function with respect to time, we need to first go through taking the rate of change of the function with respect to the variables. Like for example, we have v, and then after that, take the rate of change of the variable with respect to time. We know that doing this, we can cancel dv mathematically, but we do it step by step using this term and following this term. Also, other than v, we also have r and h. So du over dt will also involve, other than the variable v, we also need to take the derivative of the function with respect to the radius, and then take the derivative of the radius with respect to time. So also that will also be applied for h. Now let's clear the screen and apply the derivative. Actually, if we do that, taking the derivative of the function with respect to 3 variables, we will have a problem, and because the only thing given here is dv over dt. If we get dr over dt and then also dh over dt, we will have 2 unknowns. But I will show you all of that, the problem of not simplifying this equation into just 2 variables. So I will show you the problem if we don't simplify this equation. So guys, before we move on to that, we can simplify this problem by passing through a plane here, and then passing through a plane here, and then we can cut this cone into half. Then actually we can see a triangle being formed here. So we can analyze the problem by using 2-dimensional figures. Actually, we don't need the whole triangle here, we only need the half of this. Okay, so that we can make ratios about the radius of the container to the radius here of the water at this particular moment. R, that is the distance of this particular point where water touches the surface of the cone to the center. So it actually looks like this. Okay, so this is the radius of the cone, nickel tank, the height of the cone, nickel tank, and this is the height of the water this particular moment. So water, this is the surface at this time. Using similar triangles, 4 meters for the radius of the tank, 12 meters for the height of the tank, and then 9 meters for the height of the water. What is RW? R here, the surface of the part of the water that touches the tank. RW is actually, you should know this, right? Transpose 9. RW is actually just 3. So we know all the dimensions, and the other given that we should also consider is This one, which can be represented as dV over dt. The rate of change of volume with respect to time is 1.5 cubic meters per minute. So again, let's rewrite the formula for the volume of the cone, which is also the volume of the water because water assumes the shape of its container. So again, the variables v, volume, radius, and height are changing. So we're going to take the derivative of the function with respect to time. Take note, we're not simplifying this, although we can actually simplify this equation that v, that we can actually remove h and make use that similar triangle to remove h, or we can also remove r. But here, this is the problem that will happen if we don't simplify the equation. So let's say here, of course, this is dv over dt for the left side of the equation. Now for the right side of the equation, we are taking the derivative of two variables, right? Variables. The values of r and h are changing with respect to time. So to take the derivative of r squared times h, we remove the constant pi over 3 already, right? We need to use the product rule, wherein first we can treat h as the constant here and then take the derivative of r squared. So we're going to use the chain rule here, wherein, okay, so it actually looks like this, the one that I showed you earlier, du over dr, and then dr over dt. Du over dr means that we are, from r squared is going to be 2r. So that means we're done with this part. And then times, because here we have times, so dr over dt. So that's how it looks like. So that's what we're going to write here. So it's 2r times dr over dt. So the first term, using the product rule, we treated h as a constant. And then now, plus the other term wherein we treat r raised to 2 as the constant, and then h as the variable that we want to integrate. So dh over dt. So why is it only dh over dt? Because h is actually raised to 1. So if we do du over dh, then du over dh is, you bring down 1, and then 1 minus 1 is 0. So this is actually, take the derivative of h is actually 1. And then after that, we do dh over dt, which is dh over dt. So that's why we have dh over dt, treating r squared as a constant. So this term, we got that. So here, after evaluating, after differentiating the function, we have dv over dt given from the problem. So we have no problem with this term. We know h, that is 9. We know r, which is 3. We know r, which is 3, so r squared is 9. dr, we don't know dr over dt. We don't know dh over dt. So we have two unknowns in this function. So there's a problem because we can actually simplify from at this point, but we didn't. So how will we simplify in order to remove one variable? Like we can remove h, we can remove r. We can just use similar triangles. So in this particular cone, the dimensions are fixed to be 4 and 12. So as water goes down, it will just have that same ratio of radius to height. It will just have the same ratio of radius to height. So what is it that we want to cancel here? So let's analyze the question. So the question is, find how fast the water level is lowering when the water is 9 meters deep. How fast the water level is height. Water level is changing when the water is 9 meters deep. So that is dh over dt. So we can simplify this equation by just volume related to height. So that means we can remove r. What do I mean? I said similar triangles, right? In terms of similar triangles, we know that this cone has a ratio of radius to height of 4 to 12. So reduce to height, 4 to 12. 4 to 12. And also at this particular moment, the water will just have that same ratio. Like here, 4 to 12, 9 to 3, that's 1 to 3, right? So we want to remove r. We can do that by, first of all, 4 over 12 is 1 over 3, right? And then transpose h here. So it's actually h over 3 is equal to r. That is the relationship of height to radius in this particular cone. So if we substitute r here, we can actually get rid of r. It looks something like this. Substitute r, which is h over 3. So h over 3 raised to 2 times h. So now, you see what's happening? So v is equal to pi over 27 h raised to 3. So that if you differentiate this, we will only have v and h, and dv over dt is already given. We know it as 1.5. You differentiate this, we can get... Okay, so I will clear the screen for you guys. But remember, it's pi over 27 h raised to 3. So let's take a minute break. Alright, so it's v. We simplified it to v is equal to pi over 27 h raised to 3. Now we can differentiate it. Take note of the application of chain rule in this differentiation. dv over dt, rate of change of volume with respect to time, also called as flow rate. Pi over 27 is a constant. So here we're going to use du over dh. So h raised to 3, differentiating this function with respect to h, is 3h raised to 2. So 3h raised to 2. So we're done with this term. Now we are going to do dh over dt, which just multiply rate of change of height with respect to time, which is unknown. dh, sorry for that, dh over dt. So dv over dt is negative 1.5. Negative because water is going out. And then 3 over 27 is 3 over 27 is 1 over 9. We just this is also divisible, a multiple of 3. And then we have h raised to 2 is 9 meters raised to 2. And then dh over dt is unknown. So here in terms of units, this is m raised to 3. This is m raised to 2. So we will cancel m. And then the units that will remain is meters per minute. So if you know how to algebra, you just have to transpose it up, the 9 up here, transpose pi, transpose 9 raised to 2, which is 81, and then we will evaluate the numbers. That will be equal to dh over dt. That is equal to, according to my calculator, it's negative 0.053. Alright, negative 0.053 meters per minute. We have here m raised to 3, m raised to 2, so m per minute, which makes sense because what we have on the other side is change of height, m, with respect to change in time, minutes. So that is the answer to the question, how fast the water level is lowering. I don't need money, guys. I need views, which will give me money. Okay, thank you for watching.